Welcome to the session number 3 from the playlist of gravitation. The topic is the gravitational potential, and this topic is in a continuation of the session number 2, in which we have studied about the gravitational field and the gravitational field intensity. So, with regards to this topic, I have written here 5 important points which will help us to understand this topic of gravitational potential. So the first point here is basically the definition of the gravitational potential. So the definition of the gravitational potential is that it is a gravitational potential at a point in the gravitational field of an object is equal to the work done in bringing a unit mass from infinity to that point. Here infinity means that we are bringing an object of say mass small m from a very far place. So in other words, we can write the gravitational potential V is the symbol for the gravitational potential, which is equal to W by m, where W is what? It is the amount of work done in bringing the amount of work done in bringing an object from infinity to that point, and small m is the mass of that object. So V is equal to W by m. W is the amount of work done in bringing that object from infinity to that point, and divided by the mass of that object. Now with reference to our planet Earth, I can write this equation, that is V is equal to minus Gm by R. Here m is what? This will be the mass of the Earth, and what is R? R is equal to R plus h, where R is the radius of the Earth and h is the distance of that point from the surface of the Earth. So with the reference to our planet Earth, this V is equal to minus G m divided by small r, or we can also write this equation as V is equal to minus Gm divided by r plus h also, where r is the radius of the Earth and h is the distance of that point at which we have brought a mass, or you can say an object of mass small m at that point. So this is the formula for the gravitational potential with reference to the Earth, and this is the formula for the gravitational potential at a point which is located at a distance given by small r is equal to r plus h. So here now the second point here is the gravitational potential is negative because the gravitational field is performing the work in bringing the object from infinity to that point. Now the third important point here is that for the solid sphere, the gravitational potential is equal to minus G into capital M by R. Like our Earth is a sphere, so at any point in space around the Earth, which is situated at a distance h from the surface of the Earth, the gravitational potential will be equal to V is equal to minus G capital M divided by R plus H, and since R plus H is equal to R, so therefore we can also write this equation as minus Gm divided by small r. Now the gravitational potential beneath the surface of the Earth, that is beneath means when we go down into the surface of the Earth towards the center. So beneath the surface of the Earth, the gravitational potential is equal to Gm divided by 2r cube, where r is the radius of the Earth, in bracket 3r square. Here capital R is the radius of the Earth minus r square, small r. Now here r is the distance of the point from the center of the Earth. Here r is the distance of the point from the center of the Earth. So this is also a very important formula from the point of view of solving the numerical problems. Now for the spherical shell, so these two formulas were for the solid sphere. Now for the spherical shell, the gravitational potential above the surface of the shell is given by minus gm divided by small r, where r is again equal to r plus h. Here r will be, in this case, the capital R will be equal to the radius of the spherical shell, and h will again be the distance of the point from the surface of the shell. So now in the case of the spherical shell, the gravitational potential inside the surface is equal to minus gm divided by r, capital R, where capital R is basically the radius of the spherical shell. And in the case of a spherical shell, the gravitational potential inside the surface is equal to the gravitational potential on the surface. So on the surface, the gravitational potential will be equal to minus gm divided by capital R. So, and this is also the gravitational potential inside the surface of the spherical shell. And here, this small r is what? This is the distance of the point from the center of the sphere. That is, if the point is lying outside the spherical shell, then r will be equal to capital R plus h here, where this capital R will be the radius of the spherical shell and h will be the distance of the point from the surface of the spherical shell. Now, there is one important relation between the gravitational potential and the gravitational field intensity. Now, the gravitational field intensity I is equal to gm by r square and the gravitational potential, as we have seen, that it is equal to minus gm by r. So if I v upon I will be equal to minus r. If I, that is, the I is equal to gm by r square and v is equal to minus gm by r. So v upon I will be equal to minus r. This is what I have written here. That is, v is equal to minus I into r, because if v is equal to v upon I is equal to minus r, then v will be equal to I into v will be equal to minus I into r. And if I differentiate this equation, that is, v is equal to minus I into r with respect to r, then dv upon dr will be equal to minus I. If I differentiate this equation, then dv upon dr will be equal to minus I, or simply we can say that dv is equal to minus I dr, or we can say that this the potential difference between 2 points in space can also be written as v2 minus v1 minus integration of within the limits of r1 and r2 I dr, where r1 and r2 are the 2 points in the free space. So this is another important relation between the gravitational potential and the gravitational field intensity. So thank you very much for joining in this session. In the next session now, I will be taking up a couple of questions with regards to what we have studied in session number 1, 2 and 3. So till then, have a nice day. Bye.